Next, let's take a look at a ring network. Now, a chain network you can think of as being the relationship between a set of individuals with a direct chain. So basically, for example, the relationship between me and my chain of ancestors. So it might be, this might be my son is connected to me, and I'm connected to my dad, and my dad's connected to my grandfather, so on. I actually don't know who my great-grandfather was. That's a chain network. In a ring network, we actually now complete the loop, which isn't a good representation of my family, I'm glad to say. But lots of other things do have this sort of relationship. And as we can see in this particular example, we have a ring of 5 nodes, and there are 5 edges, 1, 2, 3, 4, 5. One thing that might be useful to do at this point is to look at what ring network like this might look like as a piece of code. For the purposes of this course, I'm going to represent graphs as dictionaries of dictionaries. The way that works is, let's take a look here. So what we're going to do is make a graph. We're going to call it a ring. We set n equal to 5, and we initialize the ring to be an empty dictionary, so just brace. Then what we're going to do is to this empty graph, we're going to start adding in edges. And the particular edges we're going to add in, we're going to loop for each number from 0 to n minus 1. We're going to make a link in the ring from node I to node I plus 1 mod n. That's going to get us the wraparound at the very end. What make link does, and I'm going to use the same definition throughout, is it takes a dictionary, a graph, and 2 nodes that we want to connect together, checks whether the first node is already in the graph, and if it is not, then it creates an empty dictionary for that node. Same thing for node 2. Then it goes to the dictionary for node 1 in the graph and says that there is a connection to node 2. So this basically just establishes the connection between node 1 and node 2 so that later we can go and test for it if we want to. So once we've created that dictionary, we can ask questions like, well, how many nodes are in the graph? And how many edges are in the graph? So I actually ran this already. You can see that the number of nodes is indeed 5, which is good because that's what we wanted it to be. And the number of edges, the way that we're calculating that is by taking a look at all the nodes in the graph. In this case, the aring.keys is giving us back a list of all of the names of the nodes in the graph. And we're going to assign the variable node to be each one of those in turn. And what we're going to do with that node is look up the dictionary for that node. In other words, look up all the connections that node has in the graph. Look up the length of that, put it together in a big list. This list has one entry for each node in the graph, and that entry is exactly how many edges that node has, which you may recall from last time is called the degree of the node. So this expression actually, from this bracket here to this bracket here, gives us a list of the degrees of all the nodes. We sum all those up, and now we've counted each edge twice, so we divide by 2 to get the total number of edges in the graph. In this case, I then printed out the actual graph itself just so you can see what it looks like. So 5 is the number of nodes. 5 also happens to be the number of edges because this is a ring. There's one edge coming out of each node and then wrapping back around to the front. And what it actually looks like internally is the list of the nodes. This could be any name at all as long as each node has a unique name. I used numbers here because it was really easy to do. So there's node 0, node 1, node 2, node 3, node 4. And what node 0 is a dictionary of all the nodes that it is connected to directly. So node 0 in a 5-node ring is connected to node 1, the node right to its right, and node 4, the node that would be one behind it with a wraparound. Similarly, 1 is connected to 0 and 2. 2 is connected to 1 and 3, and so on.